So in this video, we'll be looking at the example of a golf ball being projected off a cliff at an angle. So the problem says that the golf ball has a speed of 30 meters per second, and it's being projected at an angle of 50 degrees above the horizontal. So we know the initial velocity is 30 meters per second, and it is being launched at an angle of 50 degrees above the horizontal. We know that it lands 60 meters below the launch position. So it's going to be below where it starts. And we're asked to find the ball's velocity on landing, which is the final velocity of the ball. And then we're asked how long is the ball in the air. So we need to know the total time. So below I already have a diagram started, and so there is this golf ball on top of this cliff. It's being projected off at an angle, and then once it's in the air, it follows this parabolic trajectory until it reaches the ground below the cliff. And so this stopping point is its final position. So our next step is to define a coordinate system for our problem. I'm going to choose to have the origin lie at the base of the cliff so that the final position of the ball is going to be y equals 0. So to the right is going to be the positive x direction. Pointing up is going to be the positive y direction. So now after defining this coordinate system, we can start filling in some of our initial values. So the initial position of the golf ball is going to be x0 is going to be 0 meters, and it's going to have initial y position, y0 equal to 60 meters, because that's how tall the cliff is. And then our final position over here, it's going to be, we are going to have a final position of xf. We don't know how far it's going to land. And it's going to have a final y position of 0 meters. We don't know how long the time takes, but we do know that the acceleration in the y direction, just like all projectile motion, is going to be negative 9.8 meters per second squared, assuming up to be positive. Now that we have our coordinate system specified and we started looking at our given values, the last given value that we haven't labeled is the initial velocity. And so the next step for that is to break it up into its x and y components. So doing that, we want to start by drawing our x component. So we start at the base of the velocity vector. We draw our x component. So that would be v naught x. And then from there, we do tip to tail. And so we draw the tail at the tip for our y component, v naught y. And we know that this angle at the base here is 50 degrees above that horizontal. Using SOHCAHTOA, we can solve for those components. V naught x is going to be equal to 30 cosine of 50 degrees, and V naught y is equal to 30 sine of 50 degrees. And so doing the math, those come out to 19.3 meters per second for the initial component in the x direction, and then 23.0 meters per second for the initial component in the y direction. So now that we've labeled all of our given values, we still need to label what it is we are looking to find. And so the first thing that we're asked to find is the ball's final velocity right before landing. And so looking at the diagram, it's going to continue on this path downward. And so it's going to have a velocity that is downward and to the right. So VF, we're expecting downward and to the right. And that should be in units of meters per second. And then we're asked to find how long is the ball in the air. So we're going to want something like T total is equal to, it's going to be positive, and it's going to be in units of seconds. Now we can move on to planning our solution. We know that in the x direction, acceleration is 0. So the initial velocity in the x direction is going to be equal to the final velocity in the x direction. The other equation that we have for the x direction is the final position is equal to the initial position plus the initial velocity multiplied by time. And so we don't know the final position, we know the initial position, we know the initial velocity, and we don't know the time. So we're not sure if that's going to be useful to us. Moving to the y direction, we're not given any information about time, and we're looking for the velocity. So we want to use the velocity equation that only deals with distance. So that is the final velocity is equal to the initial velocity plus 2 times the acceleration multiplied by the displacement. And then we're asked to find how long is the ball in the air. And so for that, again, we know the distance, so we'll just use the position as a function of time equation, which is y, the final position is equal to the initial position plus the initial velocity multiplied by time plus 1/2 the acceleration multiplied by the time squared. So let's go through and check what we know and what we don't know. We don't know that the final velocity, we're looking for that. We know the initial velocity, we know the acceleration in the y direction, and we know the initial and final position. So one equation, one unknown, we can solve for that. Then in the other one, we have the final position and initial position, we know the initial velocity, we're looking for time, we know the acceleration in the y direction, and again, we're looking for time. So one equation, one unknown, we can solve for that as well. So we're actually not going to need the equation in the x direction after all. We can use the y direction and the fact that we know the velocity, final velocity in the x direction to solve for everything. So we're going to start off by solving for velocity in the y direction using the first equation. Substituting everything in, we get that the final velocity in the y direction is equal to plus or minus 41.3 meters per second. We know that the velocity should be pointing downwards since it's traveling downwards, and so we choose the negative value from the square root. So we know that the velocity is negative 41 meters per second. The other thing we need to determine the overall velocity is the velocity component in the x direction. We know that since there's no acceleration in the x direction, because this is projectile motion, we know that the initial velocity is equal to the final velocity, which is equal to 19.3 meters per second. So we know the component velocity vectors, so we need to add them to get the resultant vector. So we start by drawing the x component first, and then we go tip to tail for the y component. And then to get the resultant, we go from the tail of the first to the tip of the second, and that gives us our overall final velocity. And then this is the angle that the final velocity is traveling at below the horizontal. And so since this is a right triangle, we obtain the magnitude of the final velocity by doing Pythagorean theorem, where we square both of the sides and take the square root. And so we find a final velocity of 45.6 meters per second. To determine the angle of this final velocity, we take theta and we use our trig rule SOHCAHTOA. So we'll take the tangent inverse of the opposite, which is 41.3 meters per second divided by 19.3 meters per second. We find theta is equal to 65 degrees. So our final velocity is equal to 45.6 meters per second, 65 degrees below horizontal. So that is how you should state your result. And now to solve for the second part for time, we use the position as a function of time equation. We substitute everything in. In this case, we need to use the quadratic formula to solve for time. So substituting that in, we're left with negative 23 meters per second plus or minus 41.3 meters per second divided by negative 9.8 meters per second squared. Now, if we take the positive sign answer, we get a negative time value. So we want to take the negative time value, or negative solution, to get a positive time. In doing so, we get a time of 6.56 seconds. And so we have a complete solution. The signs are as we expected, because 65 degrees below the horizontal is down and to the right, where 90 degrees is completely down. So if we back off of that, we are down and to the right. We have meters per second for velocity and seconds for time. And finally, is this magnitude reasonable? Well, we started off with an initial velocity of 30 meters per second, and we are falling below the starting point. So we expect the velocity to have increased. So this does seem reasonable.